Hey everybody, how you doing? We're back. We're going to do some more statistics. This time we're going to be doing the least squares regression. So the objectives are to be able to find the least squares regression line and use the line to make predictions, to interpret the slope and the y-intercept to figure out what they mean in a particular scenario, and we're going to use the same scenario from the last video, and to compute the sum of squared residuals. So we have some sample data here. The ordered pairs are vertical. So this is an ordered pair, 0, 5.8. Looks like this. This is just an ordered pair. And then we got another ordered pair, 2, 5.7, and so on. That's the relation that is given to us. We don't know what it means. It's just some data where x is the explanatory variable and y is the response variable. Given that information, we are asked to find just some equation that gets pretty close to these points. So one way to do that, as shown in step A, is to take two ordered pairs. So they're taking 2 and 5.7 along with 6 and 1.9. Find the slope by doing the change in y over the change in x. So whichever y value could go first, they did the 5.7 first minus the 1.9. I could do it the other way. I could say 1.9 minus 5.7. So if I'm doing that, 1.9 minus 5.7, then I've got to do the x values on bottom, which is going to be 6 minus 2. And when I calculate that, I get about negative 0.95, which is the exact same thing that they got. So it doesn't matter which order you subtract in, because you'll get the opposite of both the numerator and denominator. And when you take the opposite of both numbers, it's like multiplying them both by negative 1. If you multiply by negative 1 on top and the bottom, it's like you didn't multiply by anything at all. So that is an m value for, let's just say these points do something like this. There's some kind of pattern there. And we're just picking two of the points. So maybe I'm picking this point, and maybe I'm picking this point, and then trying to find the line that passes through them. Maybe that's not the line of best fit, but it would still be a line that passes through at least a couple points in a set of data. So that is the slope. And using point slope formula, which is y minus y1 equals m times the quantity x minus x1. You just pick either one of the ordered pairs and substitute in your m, which is negative 0.95 times x minus the x coordinate. Well, they use the 2 and the 5.7. They use this ordered pair. So they're subtracting, right here, they're going to subtract the x-coordinate. The x-coordinate was 2, so minus 2. And then right here, we're subtracting the y-coordinate, and that's 5.7. So negative 5.7. And that would be a line that would fit two of the points, maybe not all of them, but at least a couple of them. It would be a decent line. You can, and you can see that down here they've converted it to slope-intercept, which is y equals mx plus b. All you have to do is take the 0.95 and multiply it by x, or negative 0.95 times x, gives you this part. Negative 0.9 times negative 2 gives you the positive 1.9, and then you just add 5.7 to both sides, and that gives you the 7.6. They're just changing point slope form into slope intercept form. So here's that situation. Here is the data from this table graphed onto a scatter plot. We got a point here, got a point there, one right there, one right there, one right there, one right there, and one right there. That doesn't look quite right. There was a point, supposed to be a point at 2, 5.7. Oh. Yeah, so they didn't quite draw this correctly. At x equals 2, y equals 5.7, this point really should be on top of that line because the line was created using that point, so it should be there. It should also contain 6 and then negative 6 and then 1.9. So one of these 2 points, whichever one is correct, should be on that line. The 1.9, the lower one. They didn't draw it quite right, but regardless, that line should have contained those 2 points. There should be another point above there. And that looks pretty good. Now you can predict what y would equal if x equals 3. You just take the equation that you came up with and substitute any x value that you want to predict. So they substituted 3. And then in simplifying that, you get that y would equal about 4.75. And we did that because we can see that there is a 3 value here. When x is equal to 3, y is equal to 5.2. But what I want to know is, does this function, the negative 0.95x plus 7.6 function, will that give me a predicted value of 5.2? And it turns out, no, it's 4.75. There's a bit of a difference there between what we expect to happen and what actually happened. So we say that the observed value at x equals 3, the observed value was y equals 5.2. What our equation predicted, what we predicted here with that equation is 4.75. You get a residual by subtracting observed y value minus predicted y value, and that's what it says there. So by subtracting 5.2 and 4.75, we get a residual of 0.45. All that means is this point on the graph is at 4.75. I wish this thing would stop. This is driving me wild. We predicted right there a value of 4.75. The table actually had a y value of 5.2. So there is a residual right here. The difference between those. Now, please make note that when you're drawing a line segment from the observed point straight up or down to the line, to the predicted value. That's super important because from any point, if I pick a point like right here, there are an infinite number of line segments that I could draw that would get me to that line. Oh, didn't mean to do that. So there are an infinite number of line segments that I could draw to get to this line. The one that you have to do when you're trying to look for a residual is the one that is straight up and down. So sometimes you go down to a line if your observed is greater than your predicted value. And if your observed is less than your predicted value, then you draw a line going up, like that. Anyway, that's how you calculate a residual. If your observed is more than your predicted, you'll get a positive residual. If your observed is less than your predicted, then observed will be smaller minus the predicted, which would be bigger, and that's obviously going to give you a negative residual. Now here's the problem. If you were to just add up all of the positive residuals and negative residuals, the positives and negatives would cancel out. So if I have really big residuals of like 100, negative 100, 5 billion, or let's just say 5 million. If I have a residual of 5 million on this graph, not on something to do with the federal budget, but something with this graph. 5 million, that is a huge residual. That line's going to extend up in space. But what if I have another residual really far down below the line at negative 5 million? What would happen if I added up all of those residuals? They would add up to 0. And that would belie the situation. If I've got residuals that all add up to a really small number, because some of them are positive and some of them are negative, think about a line of best fit. It's got some points that are above the line and some points that are below the line. That's the whole point of a line of best fit. You want a line that is pretty much in the middle of a set of data. So half of them are going to be above the line and half are going to be below. So you're going to have positive residuals and negative residuals. The further those points are away from that line, the bigger the positive and negative residuals are. But either way, when you add them all up, it's very likely that they're going to be a very small number, even if they're really far apart. So how do you prevent that kind of negation of value by adding positives and negatives? Well, you do it by squaring. So, for example, if I have residuals of negative 10, 10, 5, and negative 5. Adding all those would give me 0 because they're two sets of opposites. But what if I squared those? So these are my residuals. I'm going to take the residuals and square them. So what is negative 10 squared? Well, that becomes a positive. Now it's 100. And if I take this 10 squared, it's also 100. They're still both positive. 5 squared is 25. And negative 5 squared is 25 also, because two negatives cancel out. Add that up, and the sum of these squared residuals is 250. The idea is to get this number, the sum, oh, that was not what I wanted, to get the sum of the residual squared to be as low as possible. That's what we want to get. We want to get the sum of the squared residuals to be as low as possible. If we can do that, then we will have the line of best fit, the best possible line. And luckily, we don't even have to manipulate the graph. Let me show you what I mean. Okay, notice here that we've got a bunch of points. That's what all these little dots are. These are just points on a scatter plot. And if I click simulate, it's just going to move the points around, right? It's just going to choose random different points. So I'm going to land on this one. This graph here looks pretty linear. And what I want to do is take this green line and see if I can position it in a way that it looks like it might be the line of best fit. And this is available in Pearson under chapter 4.2. It's under the multimedia library or something like that. I think that's what it's called. So if you open that up, go to chapter 4.2. It's an applet. It's called Regression by Eye. All right, so I'm just going to move this around until I think it looks good. I don't know. What do you think? Something like that? Looks pretty good? Okay, well, what is going to happen here? Oh, I don't know if you can see my cursor, but I'm going to hope you can. I'm going to hope that you can. If I were to draw a line segment straight down from this point to the line, it's going to have a particular value. If I draw a square out of that same length, whatever that length is, I make a square out of it. The area of that square is essentially the residual squared. So if that residual was 3, the area of the square I'd make would be 3 times 3, which would be 9. So that area would give me the area of one residual value. I could do the same thing here with this point. That residual would be a little bit bigger. Find the area and add those two things. Then I would add the squared residual for this point, and for this point, and for this point. That's a big one. This point's kind of small. make a square out of that little residual. This one's huge. So that one I'm a little worried about. But the idea is I'm going to keep doing that and add up all the residuals. Maybe I'll move this a little bit. Maybe that looks a little better. And I know there's a point over here that we can't really get to because I can't zoom out on this graph. Okay, so what I'm going to do is see what the program tells me that the sum of all those squared residuals is. And here it is. It's 168.2909. The very best I could get this number is this red number, 112.8. So I'm off by quite a bit. Let me see if I can move it around to get an even better line. Maybe that, maybe move this one. Ooh, there we go, it's decreasing. 112 point something. It's going to be nearly impossible to get it perfect. Got 114. 113. That's pretty good. 112. That's really, really close. So you could play with that as until you got exactly 112.8, or it's probably rounded, but that'd be a pretty good guess. But wherever you initially draw that line, it's probably not going to be great. It's not going to be a really good line. If you click right here where it says regression, it'll show you the perfect line. And you can match them up to see how close you can get. So that is the best line for the smallest squared residual sum. All right. The least squares regression line is the line that minimizes the sum of squared errors or residuals. This line minimizes the sum of the squared vertical distance, not horizontal, not diagonal, but straight vertical, up and down to get onto that line, between the observed values of y, that's the values in the table, and those predicted by the line. And we call the line y hat. That's what we call the least squares regression line, y hat. So the easy way to remember that is just to minimize the sum of the squared residuals. This is the formula that you will use to calculate the line of best fit. Remember, a line can be written in the form y equals mx plus b. In our case, we're not just using the letter y, we're using y hat to stand for the function for our line of best fit. Instead of m, they're using what's called b1. X is just an x value, and instead of b, they're calling it b sub 0. This is the formula to calculate b1. This is the formula to calculate b sub 0. Notice that if I take that equation for b sub 0, if I take that equation, and if I add b1 x bar to both sides, b sub 1 times x bar, those cancel out, and then I get y bar equals this, which is b sub 1 times x bar plus b sub 0. Notice how similar that is to the equation for the line of best fit. What is going on? There we go. Notice how similar that is to the equation for the line of best fit. So if you substitute in the equation for that least squares regression line, I like to call it the line of best fit. Best is the most important word. There's no better line than that line. If you replace y bar with, or y hat with y bar, and you replace x with x bar, and then try to isolate b sub 0, then you get this equation here. That's just something that I noticed. All right, so where are we going to get this information so we can fill in this equation? we're going to take this equation and we're going to fill in b sub 1 and b sub 0. Well, we get them if we know these three things. If we know those three things, r, s sub y, and s sub x. If we know r, remember that r is the correlation coefficient. We just did that in 4.1. Sx is the sample standard deviation for the x values, and S sub y is the sample standard deviation for the y values. We did that in 4.1. I made an Excel spreadsheet and we calculated it. So that's easy. We just we just make a table of values. From the table of values, we calculate the S sub y and the S sub x, and then and we also need, down here you can see we need x bar and y bar. If we have those things, the sample standard deviations of y and x, and we've calculated the correlation coefficient already, we can use those to figure out what b sub 1 is. That's the slope of the least squares regression line. Then we can take that b sub 1, put it into this equation, and it will spit out b sub 0, which is our y-intercept of the least squares regression line. It's really quite easy. Let's give it a try. We already know that. So notice this data, which was, drilling. Where do we start drilling? How many feet below the surface of the Earth? So if we start drilling 50 feet below the surface of the Earth, it's going to take us an extra 5.99 seconds to drill 5 more feet. Or not seconds, 5.99 minutes, excuse me. So let's go back to our table. Okay, so we've got our table here. These were the values from that table. Let me highlight those yellow. We calculated these values here, and we calculated an R value here. Let me make that a little darker so we can see a little better. There we go. So the mean value is 120, for the x values is 126.25. I need that for my b sub 0 calculation. The mean for y bar, is 6.986 about. I need that also for the b sub 0. For b sub 1, the slope of that least squares regression line, I need r, which I have right here, 0.773 about. And I need both the sample standard deviations, which I have right here, 52 point something and 0.78 something. I just got to take these 5 values and move them over to my worksheet where I'm doing my work. So let me do that. Okay, so I've taken these 2 functions and I've written them on the next slide. And here they are. B sub 1 is equal to R times S sub y over S sub x. In other words, it's the correlation coefficient multiplied by the quotient of the sample standard deviation of y over the sample standard deviation of x. Whatever that b sub 1 value is, it gets substituted into the b sub 0 formula. So I don't know what that value is yet. Once I do, I'll substitute y bar and x bar. Those are the sample means, the means of the x column and the y column from the table. And let's go ahead and calculate this and see what we get. The R value, the correlation coefficient from the work that we did last time, was about 0.77282. I specifically chose 5 decimal values because the more values you use, even though that's rounded, it's not perfect, but the more decimal places you round to, the less rounding error you're going to have in the end. And then I'm going to multiply by S sub y over S sub x. Well, S sub y yesterday was 0.78077. You can go back and look at the video about 2 minutes ago when I had the Excel spreadsheet up. And S sub x, the sample standard deviation for the x values, was 52.22874. So I'm going to calculate that now. What is that equal to? Well, 0.78077 divided by 52.22874 is that decimal, about 0.0149, blah, blah, blah. I've got to multiply it by r, which is 0.77282, and I get about 0.011553. 0.11553. That is about the B1 value. So let me go ahead and circle that. That is B1. And notice that B1 goes in this position right here, which means I'm going to substitute this number into this position. 0.011553. Now I need to just substitute x bar at the end right here from the table, or from the Excel spreadsheet we did yesterday. We got that it was 126.25, and the y bar, the sample standard, or sorry, the sample mean for y was 6.98583. Again, I'm going to use my calculator to do this. So I'm going to do 6.98583 minus, now I'm going to do parentheses because I'm multiplying two things, 0.011553 times 126.25, close parentheses, and that's exactly what I want to calculate right there. Hit enter, and it tells me it's about 5.52726. 5.52726. So that is B sub 0. Now I know what my equation is for the line of best fit, for the least squares regression line. Y hat equals, remember it's B1 times X plus B sub 0. So that means Y hat is B sub 1, 0.011553 times X plus B sub 0, which was 5.52726. That is the perfect equation. As you can see here, they got about the same thing. They rounded it a little bit differently. A quick way to get this equation, remember, I want you to be able to do this math on your own. I want you to prove to yourself that you can get the correct value without using the shortcut. Once you've got a value for B sub 1 and B sub 0, you've got B sub 1, you got the slope of the least squares regression line, and you've got so you've got the slope of the least squares regression line, and you got the y-intercept of the least squares regression line. Once you've found those two things, then go on to Desmos and do what I'm about to show you to double check that you got it correct. So you enter in your table like we did here, and you type in, normally we do y equals mx plus b. You remember you have to change three things. So x isn't really x in our table. The x values are called x sub 1. So I'm going to put a 1 there. The y values are called y sub 1. So I'll put a y sub 1 there. You don't need to do anything special for the subscript. It'll just type 1 right after the y, and it'll know what to do with it. And change the equal sign to the tilde. It's just to the left of the 1 key. Just push the shift button and then that button. And there is the least squares regression line. The Desmos will do it for you. The calculator will do it for you. It's great. Notice down here what the m and the b values are. The slope of that line, that least squares regression line, is 0.011553. Does that not look familiar? The b value, the y-intercept, is 5.52727. Now, those are very, very close to what I got. The only thing that was a little bit off, was this value. And I have a 6 here, they have a 7 there. That was it. I mean, 5 decimal places in, you're doing pretty good if you get that close. I don't think Pearson's going to ask you to round to 5 decimal places anyway. It would probably ask you to round to 2 or 3 or something, in which case you're golden. So part B here says, well, predict the drilling time if the drilling starts at 130 feet. Okay. Well, what I'm going to do is I'm going to make a function called d of x. That means, I'm sorry, not d, let's say t of x. T stands for time. How much time will it take to drill 5 feet? Well, if I put in equals mx plus b, notice that that graph is right on top of the red one. Now what I can do is calculate what this value is here at 130. I could just kind of move up and down the line until I find it. That'll work. But another way to do it is to just make a function and just type in t of 130. And it will give you a pretty good estimate. So about 7.03. That's how many seconds, or I'm sorry, that's how many minutes it's going to take to drill 5 feet if we start drilling at 130 feet below the ground. So if I've got my drilling equipment on the surface of the earth and I've already dug a hole 130 feet down, if I want to keep drilling down into the rock that's 130 feet down, it's going to take me, on average, from that point, about 7 minutes for every 5 feet I want to go. That's what this says. Is the observed drilling time at 130 above or below? Well, at 130, we said the predicted was about 7.03. The observed was 6.93. So as it turns out, the observed drilling time is below average. So that means if it actually took us 6.93, then we're beating the curve. We're beating the average. And part D, it says draw the least squares regression line on a scatter diagram. Well, there it is. You can also see, you can also make it on Desmos. That works as well. Now let's interpret these values. So what does that mean? If y hat equals 0.0116x plus 5.5273. Let's start with this value, 5.5273. You know that's the y-intercept. The y-intercept is when x is 0. So what is on the x-axis of our graph? The x-axis represents the depth that drilling begins. So that 0 for x means that we begin drilling at 0 feet. So the y-intercept just means we haven't dug any hole yet. We haven't started anything. Our drilling equipment is on the surface of the earth and and it's solid. We haven't even begun to poke a hole into the earth yet, but we're about to. Remember that the y value, as you can see over here, represents the time it's going to take to drill 5 feet. So the y value is the time to drill 5 feet, and it's in minutes. In other words, the prediction is that if we were to go to this particular place and put drilling equipment at the very top, where there's not a hole yet, and begin to dig, it would take us about 5.5 seconds to get that first 5 feet down underground. Now the slope is the change in y over the change in x. That's what the slope is, and we're calling the slope B1. Well, the change in y is the change in time. Excuse me. And the change in y over the change in x, I know to be this decimal. And I can just put that decimal over 1. So 0.116, that's positive, right? So that's 0.0116 more what? Well, what are the units for y? It says time, and we said this was in minutes. So in other words, it takes that many more minutes every time we want to do one of what? Well, every time we want to have one, and was this, what are the units here? Feet. Yeah. So these represent feet. In other words, if we were to write this out, for every extra foot of depth that we begin drilling below the surface, we add 0.0116 minutes to the time needed to drill 5 feet. That is what that's saying. 0.0116 over 1 means that it's going to take 0.0116 more minutes to drill 5 feet every time, or for every foot below the ground we start. So if I start 10 feet below the ground, multiply that number by 10, and we're going to add that to the 5.5273. Because we start out it's only going to take about 5.5 minutes. But every extra foot that we begin drilling, maybe we've already got a hole that's dug partway underground, you add that many feet times 0.0116. And that's how many more minutes you'll add to your 5.5 minutes that you started with. I'll leave this here so that you can read it for a second if you want to pause the video. Okay, so the question is 0 a reasonable value for the explanatory variable, for the x value? If x is 0, we said we predicted a y-intercept of 5.5273. And yeah, that's kind of reasonable, right? Because if we go back to the table, 35 is pretty close to 0 compared to 190. And at 35 feet starting depth, it took 5.88 minutes to drill an extra 5 feet. So 35, at 35 feet, it took 5.88. And those two numbers are pretty close, and these two numbers are pretty close. So that seems perfectly reasonable. Be careful that you can't make any predictions about values that are outside of the scope of your model. In other words, I've got these data points right here, and they go up to about 190. If I type in T of 300, it says that if I start digging 300 feet below the surface of the Earth, it should take about 9 seconds. Sorry, not 9 seconds. About 9 minutes to dig an extra 5 feet, 8.99. So about 9 minutes to drill another 5 feet. That's no good. That doesn't work because 300 is further out here. 300 is out here. That's that point value right there. 300, 8.993. That is outside the scope of the data points that we collected. The only thing we can really predict with any kind of decent accuracy is values within this scope. So maybe I didn't have anything on this table at 100. So if I want to predict starting at 100 how long it would take, there's my answer. It would take about 6.683 minutes to drill 5 feet, according to this model. I can predict that with a decent accuracy. I can't do it for values that are far outside of my outside the scope of my model. We just don't know. And this just says that we can use that regression by eye applet to illustrate the fact that the sum of squared variables for a least squares regression line is less than the sum of squared residuals for any other line. If I go back to that applet and I show the regression line, let me show it, it's right here. I can move this green line anywhere I want, but I'm never going to get a line whose sum of squared residuals, that green value right here, I cannot find a line that's going to give me a sum of squared residuals that is less than the regression line. That red line is the perfect line. There is no better line to use. And that's all this says. You can play with that to your heart's content and see if you can find a better line. I bet you won't. That's it for 4.2. I'll come back with 4.3 as soon as I can. I'm going to be pushing back assignments because these are a little bit late. I hope you can forgive me, but I hope you learned something from this lesson. Ooh, that wasn't good. Be sure to hit that subscribe button if you care about that sort of thing. I really don't. So, but I'll talk to y'all later. Take care.